Excellent. Well, good evening, everybody, and welcome to Our Universe Revealed. This is the public talk series for the Department of Physics at the University of Notre Dame. My name is Jonathan Crass, and I am the series coordinator. Whether you're joining us for the first time this evening or one of our returning attendees, it's great to have you with us tonight. If you want to find more about the series and find out about our upcoming events, you can do that on our website, which is at nduniverse.org. Tonight, we have got the first installment of our what we're calling the Hubble at 30 series, which over the next couple of days, we're going to explore some of the history, some of the science, the technical details, and the servicing missions of the world's most famous space telescope. I'll talk a little bit more about those later on, and the details are also on our website if you want to take a look there and find out more about the events that we have coming up. Tonight, it is my absolute pleasure to welcome Dr. Carol Christian to Our Universe Revealed. Carol is the Hubble Space Telescope Outreach Project Scientist, and she is based at the Space Telescope Science Institute in Maryland. In her role as the Outreach Project Scientist, she's responsible for the scientific accuracy of the information from Hubble, and that's the information that's produced for students and educators, the media. Many of you will have seen stories in the media, and also the wider general public. In addition to her outreach work, she's also an active researcher. She works on several programs investigating studies of stellar clusters, groups of stars, and other galaxies. So before we launch into things, welcome to Carol. And the format this evening is going to be a presentation from Carol, followed by questions from you, the audience. So while you're watching live, you can submit questions at any time. And you can either do that as we go along, or you can do them at the end, whatever you prefer. To do that, I will share a link with all of you either in the Zoom chat, if you're watching via Zoom, and in the YouTube chat. You can also find this on our website on the event page, so you can submit your questions there. You can also, if you're on Zoom, use the Q&A feature at the bottom. Whatever's easiest for you, we'll be watching them all, and we'll do some questions for Carol right at the end. So, without more ado, on with this evening. Carol, let's see if we can get the screen sharing up and see your talk. And just to stay before we launch in, it's really great to have you with us. I can't think of a more qualified person to give us an introduction to Hubble and its capabilities.
Thanks. And you can see my screen?
I can indeed.
Okay. Thank you so much for that nice introduction, Jonathan. And I just wanted to put in a word. I had actually, when I found out that there was interest in having someone from Hubble give this talk, I volunteered because my brother went to Notre Dame. He's an aerospace engineer at Rocketdyne. And so I told him, you know, he's a Notre Dame, you know, he wears green all the time, green shoes. You know, we celebrate Notre Dame a lot. So I actually asked to give the talk.
I'm glad to hear it. Before we launched, I'm just going to say looking ahead to the event on Friday, we also have another Notre Dame alum linked to Hubble, and that's Michael Good, who was an astronaut on the final mission. So it seems Notre Dame's got lots of links to Hubble.
Yes, absolutely, which is a good thing. And Rocketdyne does shuttle engines, so there you go. So I just wanted to say one word about Space Telescope Science Institute. What it is a institute, a research institute, part of a consortium called ARA. We don't have to go into those details, but anyway, ARA runs a bunch of observatories. Space Telescope Science Institute was founded basically as an independent research institute to run the Hubble Space Telescope. We now are about to launch James Webb Space Telescope in October of this year. And we're also working on the Roman Space Telescope, Nancy Grace Roman Space Telescope, that we hope to launch in 2026. So onward, 31 years of operation of Hubble, a telescope that was supposed to run for 15 years. Okay, I need to forward. There we go. So I'm going to give you a little history, and then, of course, the science. Really, Hubble's all about the science. We've done a lot of science, and we have a bright future ahead. Lyman Spitzer was a scientist who was thinking hard about what kind of resources we could use in space for astronomy, take advantage of the space program. And in 1947, he wrote this paper, and then he worked on this for 40 years afterwards. And this is just a note about his 1946 about his paper. And the second person I want to mention is Nancy Grace Roman, and we're very happy that we're now going to have a telescope named after her. She was very active research in stellar physics, and then she worked at NASA, where they asked her to establish the space astronomy program, which she did. And so she basically created the space astronomy arm. And her last great act was, she worked on many very interesting orbiting astronomy telescopes, but her last great program that she managed was the Hubble Space Telescope, and she worked very hard to promote it, and we are very grateful to her for that activity. So what's the story of Hubble? From idea to launch, as we call it, we have in 1946, the idea starts to germinate. Lyman Spitzer's talking this up with his colleagues. At some point in there, NASA gets established, and then Nancy Grace actually comes in around the 60s and 70s and starts the space astronomy program, and then the National Academy recommends it. The public, as well as the scientific community, of course, was interested in it, and so was supporting it. And then the proposal went in, and then it takes a long time to build a telescope. It used to be called the Large Space Telescope Project. And in 1985, it is completed. And you see this nice launch picture, but that's not really how it went. There's a space telescope before launch when it was completed. What happened in 1986, although we were anticipating the launch of Hubble because it was completed a year before, was a Challenger. So that halted all the shuttle launches, a big congressional inquiry. And then eventually, several years later, at the end of the investigation, the shuttle started launching again. And on April 24th, 1990, Hubble Space Telescope was launched on Shuttle Discovery. So then with this joyous launch, this long road from the 1947 to 1990, the first light indicated sort of terrible image quality. And this is what the images looked like. It's bad, but actually all the light in the background is actually not very high in intensity. So some bright fields could actually be observed. And in that case, the true nature of the image quality was revealed. But you can see down here, a big mirror, it was being polished. And what was the problem? The problem was that the test fixture was actually incorrectly put together. And this led to a tiny flaw. And so the mirror, though nearly perfect, was just off a little bit for its secondary mirror. So when the telescope was assembled, it had a flaw. So what do we do about that? Well, all kinds of scientists and engineers. I, at the time, did not work for Hubble, but I did know an optical engineer who was really brilliant. He was actually Canadian, and he said, I know what this flaw is. We can solve this. It was actually, spherical aberration is actually a pretty easy in the sense of if you had it on a ground-based telescope, it would be easy. Anyway, so engineers and the scientists knew how to correct it pretty quickly. The rest of the story was, how are we going to correct it in space? And so at the time, because we had already built Hubble and the shuttle hand in hand so that shuttle could service the telescope, a new instrument, the Wide Field Planetary Camera 2, COSTAR, which is an instrument which was inserted into the telescope with a mirror correcting, well, an optic, more of a lens and a mirror. And actually, we took advantage of the first servicing mission to put in new gyros and new solar arrays, because the solar arrays were actually flopping around and actually moving the telescope. And this is the crew, the picture of the crew. Actually, just to point out, Jeff Hoffman was actually an astronomer. So it was a real thrill to have an astronomer up there fixing the telescope. We've had many astronomers. And to our delight, the first image of the famous M100 was the picture that you see on the left, which was a big disappointment. And then the correction, which was made in 1994, and the first servicing mission is the middle picture. But the true nature of the image quality of the mirror was then manifest when we launched Wide Field Camera 3, actually in 2009, but an image was taken of M100 again, and it actually showed that the image was much better than we were able to detect with the previous instruments. So we have the most, and this was part of the reason that we could improve the image quality and the performance of the instruments, because Hubble was made to be serviced. So you can see the difference down on the lower left, and this is a picture, of course, of the astronauts doing the repair. So a lot of engineering and push and cleverness and scientific drive repaired the telescope. And then I have here this slide that shows that the telescope has been visited 5 times, and in each case, things were upgraded. Instruments were upgraded, gyros are always upgraded, the fine guidance sensor, which helps guide the telescope, power supply, that was probably one of the most heart-stopping, because the whole power of the telescope went down. So it's like shutting your whole house down and hoping that it comes back up without being actually able to do anything if it doesn't. So the heart stopped for a while, but it came back up fine. And then the last SM4 replaced a lot of stuff, both things that made the telescope work plus instrumentation. And this slide has always had this deorbit mission thing on here, but I put someday because we're not ready to deorbit. The telescope is a beautiful telescope and is performing it as well as ever. So as I said, for 5 times, there have been more than 1.5 million observations with it, 17,000 refereed papers. This is the most productive science instrument that has ever been created in the history of mankind, and nearly 1,000 PhDs have been done with Hubble data. So let's talk a little bit about the science. Of course, I'm starting with the solar system. All kinds of data have been taken. For example, in Jupiter, looking at the evolution of the red spot, it is shrinking. Also, these beautiful whorls and clouds are Jupiter is revisited to look at Jupiter and see how the evolution of the atmosphere has occurred. We've always had great images of Saturn, seen it edge on, and then Uranus and Neptune, which are shown in the lower right. We've seen aurora, storms, all kinds of interesting phenomena. So it's been great for the solar system. We've also observed Mars several times, and both dust storms and not dust storms. So it's kind of in the weather channel for Mars. We've also looked at outer solar system objects like comets. Here's one that's splitting up. Here's another one which was more recent. And then here's one that's very curious, which is a binary. You'll hear more throughout the week on the science done. So I'm really racing through the kind of science that's been done. Some of the exciting stuff that was never anticipated was the observation of extrasolar planets. Here's just a few. We know of over 4,000 extrasolar planets, and so Hubble has been used to characterize those planets. So my little icons show that, for example, the icon means that K2, which was a Kepler discovered exoplanet, has water and it's a nice temperature. So a very pleasant planet. It's not clear whether it's rocky, but it does seem to have water vapor in its atmosphere. Unfortunately, WASP-121b has magnesium in its atmosphere, and it's bloody hot, and iron is bloody hot. K13bc is another Kepler discovered exoplanet. It's hot on the side, which is locked. It's locked tidally locked to its parent star. And it actually is in a very interesting system that has a second star. and it has titanium oxide, which is that white stuff you put on your nose for sunscreen. Anyway, it is a gas on the very, very hot side, and then winds transport the material on the other side, and then it rains out because it's very cold over there. So really bizarre exoplanet. And then we call Ogle 2007 blah 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 Tatooine because it actually circles a binary star like in Star Wars. Other things, I just wanted to put this note. This is a very unusual thing that was brought up to me, that Hubble and JWST, which JWST will launch later this year, are going to be used to look at a number of objects. You know, people are just chomping at the bit to see things at JWST, exoplanets, distant galaxies, solar system objects, all kinds of science will be done. And we're going to be very fortunate to have those telescopes operating at the same time. One of the really clever things that you might not hear later in the week is that has been proposed by people who are thinking about it, that HST and JWST could actually be used as a survey telescope. So you have HST and JWST, and you might actually be able to get much higher resolution using the two together because they will be separated in space. And that long baseline can give you higher resolution. So we'll see. We'll see if we can do that in the infrared. It's a cute idea. We'll see if such a proposal eventually goes in, and if some of the exoplanets are resolved and new exoplanets found from this high resolution. So innovative thinking is going on all the time based on the previous dramatic results, but people are always thinking about, what about this, what about that? And we say in the Hubble world, if it can be imagined, Hubble can observe it. Moving out, in our galaxy and in other galaxies, there's lots of star formation. That largely what makes galaxies shine brightly. And this is my field, star clusters. This is a star cluster that's actually in our galaxy called Westerlin 2. And if you look carefully, you see it's actually a double star cluster. And what's happened is all these stars have formed and out of this material, and it's pushed that material away and revealed the star cluster. And then lo and behold, there's a second star cluster. So we're trying to understand which of the two clusters formed first, and then the second one probably formed out of the remnant material. This is a cluster that's actually a tarantula, which is actually in a companion galaxy to our own. So star clusters are really beautiful. I could show you hundreds of these beautiful images, but I'll let you find them on our website. Other star clusters which are really interesting are called globular clusters. These are remnants of the clusters I just showed you are relatively young and just forming. Globular clusters are much older. They're remnants of the early days when the galaxy formed and when the universe formed. So understanding these tells us a lot about how the universe formed. And we're learning a lot. This diagram is just, I won't go into the details, but it's a way of determining the age. The other thing is very interesting is we've been able to actually, with the high precision imaging of Hubble, actually see motions within globular clusters and determine velocity. So this is something about the orbital velocity. That's a remarkable observation, and never intended. That was never intended when it was proposed to do that kind of science. And here's a smattering of the kinds of galaxies we look at, all different kinds of galaxies, spiral galaxies, irregular galaxies, also ellipticals. This is actually from a study that I'm associated with that looks at star clusters, which I showed you before. Now, all these things here are star clusters in all of these galaxies, and we're trying to understand what kind, we know the kind that are in our galaxy. What about these galaxies? What kind of star clusters do they have in them, and what does this tell us about how these galaxies are formed? Moving on, further out in the universe are clusters of galaxies. So all of these things here, except for this thing and these things that have these bright diffraction spikes from them, all of the things you see in here are galaxies. And this happens to be a very massive cluster. It's got a very massive object in the center and lots of other galaxies. And the arcs are caused by the gravitational field of this cluster of galaxies. So it acts as a lens and it distorts the background galaxies. Why do we care? Well, it's an interesting test of Einstein's theory of relativity. But in addition, by actually in detail looking at these arcs, we can tell something about very distant galaxies. These are the galaxies that JWST will be looking at a lot. So we can actually push Hubble much deeper than we thought we could by using these lenses. That was also something that was never anticipated as a science, but there are a lot of examples of this, of these deep fields and probed by this lensing effect caused by gravity that helps us see further out in the universe. Remarkable kind of science. Another thing that we were supposed to do was measure the Hubble constant, which is the expansion rate of the expanding universe, which we've done to about actually 2%. And in the process of doing that, it was discovered that if we look back in time, that the universe is actually expanding. So now there's a big push to understand it. There are measurements of nearby galaxies, trying to look at more distant galaxies, compare them, measure the distances very carefully. And what happened is that in this little graphic, I won't go into the details, but when we look at things that have stars in them, we get one answer for this expansion rate. And when we look at the early universe, measured through the radiation of the universe and other measures, we find there's a big discrepancy. And this is a problem in the fundamental physics of the universe. So we have the expansion, which we don't know what causes that. And now we have this problem that the way you measure the expansion gives you a different answer. Why? We don't know. It has to do with physics. So we're challenging the physics that we know by using the Hubble Space Telescope. And the last thing I just wanted to bring up is what we call multi-messenger astronomy, which is we have a wide number of receivers, the optical, infrared, but we also have gamma rays, X-rays, and now we have gravitational waves. And it's like suddenly we discovered a seventh sense. We have another way of sensing what's going on in the universe that is not sampled by normal telescopes. So that's a new field too. And Hubble is working hard on working with other facilities to understand that. Okay, now I'm just going to have a couple of things that I'm going to talk about is that in addition to the great engineering and science challenge that Hubble represented and the achievements in making it a useful telescope, the great science, you're going to have to wait just a minute. I have a dog who wants to come outside. The science that we talked about, and you'll learn more about this week, Hubble has affected the culture in ways that telescopes never have. So I want to give you some examples. The classic example, the old example, is in 2000. The Pearl Jam album cover used one of our, the Hourglass Nebula, used it on the cover. We were like, whoa, that's pretty amazing. Well, there's more examples. We have examples of paintings. Here's one, a painting based on the Eta Carina images of from Hubble. This is a quilt. There are many quilts. Lots of people make quilts based on Hubble observations. This is the Bubble Nebula, which was one of our anniversary images. Somebody made a quilt based on that. You'll recognize this field. This is the Eagle Nebula, the Pillars of Creation. Someone made a beautiful quilt based on that. There's fashion. I actually have a scarf like this and a pair of tights like that. I have no dresses like that. Anyway, lots of fashion based on Hubble imagery. You can buy all kinds of dog t-shirts with Hubble imagery on them. I'm a dog aficionado. Ebooks, educational resources based on Hubble discoveries. We also have had some really fantastic, very creative art exhibits where artists take a look at the images and then they give an impression, what they thought of when they looked at the images. So here are some examples of, this is mostly planets, the solar system, and these are exoplanets. And there's actually a piece of the solar array that was returned to Earth when the solar arrays were replaced, actually in this painting provided by the European Space Agency. Here is, this is a really nice example of an exhibit that was done by student art, and I was responsible for this exhibit. We had a big meeting in Adelaide, Australia, and I worked with a art school, and the art students picked out what images inspired them, and then they made, this is actually combined, this is a photographic montage. This is photography too. This is a painting, and this is a silkscreen, I believe. So people just have, it just inspires amazing imagination in people. And then finally, I'm just going to show you this. There are stamps, all kinds of things that have come from Hubble: tattoos, guitars, exhibits, books, poetry. Google honored Hubble, movies, more art exhibits. This is a science museum in Baltimore, and then in New York, more paintings, and then this is the museum in New York City that had a Hubble exhibit a few years back with the Enterprise, not Discovery, but the Enterprise in the exhibit. And I will stop there, and I'm happy to entertain any questions you may have. And I think I did due diligence on the time. It was very fast. It's just a little taste of what Hubble has brought to society and the scientific community and engineering community, but I hope you enjoyed it.
Excellent. Thank you very much, Carol, for the great talk and introduction. I'm just going to give you a slight break before we launch into questions. We've already had quite a lot come in, so it's great. Feel free to submit them either using the Zoom Q&A or the link or the YouTube chat, whatever works for you. I'm watching all of them right now, so we can answer those questions as they come up. And just before we launch into all of that, a quick reminder, as Carol mentioned, we have some other events coming up in the next couple of days. We're going to, tomorrow evening at 6 p.m. Eastern time, be digging more into some of the behind the scenes and how we do science with Hubble. And we'll have some scientists that have used the facility. We have some of the managers who manage the day-to-day operations of the facility, how we get data down. So we're going to be delving into that tomorrow at 6 p.m. And that'll be with a panel of people where we'll be able to do quite a bit of Q&A as well to try and answer the questions, the things you want to know. And then on Friday, we'll be talking about that final servicing mission with former NASA astronaut Michael Good. So he'll be giving a first-hand perspective on what it's like to go out and service Hubble and all of the exciting things that come with that. So you can find all that information on our website, nduniverse.org. Anyway, back to this evening. So I'm going to try to clump some of these questions together. There's been some good ones on the technical side. And so these relate to both where Hubble is now. We've had 5 servicing missions. Why can't we go and service Hubble again? And, you said about deorbiting it. Why do we have to deorbit it? And would there be any benefit for moving it to a different orbit or sending it somewhere else in the solar system from Mars? Would we get a better perspective? So it's kind of thinking of the future. Why can't we kind of service it and those kind of things?
Okay, straightforward answer is money. It's technically feasible. And in fact, on the last servicing mission in 2009, we have put a grappling fixture on the back end of Hubble so that it can be grasped. That has 2 possible uses. One is that the Hubble orbit actually degrades due to there is a little bit of atmosphere up there. So there is drag on the spacecraft, and it is slowly spiraling towards very slowly. And it has been boosted, but it is slowly degrading. Problem is that many of the parts of Hubble, when it deorbits, may burn up in the atmosphere, but the 2.5 mirror will not. And that is a hazard to life and property on this planet. So NASA has to allocate funding to make sure that the deorbit is safe, because you can't have that mirror coming down in somebody's backyard. So it has to be a controlled re-entry and deposit, likely in the ocean. You know, it's too bad because we won't have it. We only have the test Hubble in the Air and Space Museum. Okay, what about boosting? The grappling fixture on the back could be used for boosting. The problem, there's actually a technical problem. The problem is that the solar arrays are too delicate to boost very quickly. It's been tried a little nudge, but they could disintegrate. So it could be boosted. People have looked at it. People have proposed it. There's nothing on the books yet. The other idea was to robotically service it, because we're not, the Hubble is in an orbit which is much higher than space station, and it actually was hazardous duty to take the shuttle up there. There's no out if you have a problem. Especially after the Columbia accident, that we actually had to have 2 shuttles ready. Shuttle has been decommissioned. There's no way to get up there to service it, except it's possible it could be robotically serviced, but it was never made to be serviced in that way. It was made to take a couple bolts off and pull out, but it was actually made, it was designed in the 70s. So doing that robotically was not, they always thought people would do that. So it would be a technical challenge. It's not to say it's unfeasible, but it could be done. To put it in an outer orbit like L2 or Mars or something, I mean, the problem is that it takes a long time to get to Mars, and it will take a long time to take James Webb to L2. The antenna, the commanding structure really is for low Earth orbit. You need a completely different set of antenna to actually communicate with it. And we'd never be able to fix it out there anyway. The other tricky thing is, if we use a lot of money of taxpayer dollars for Hubble, we don't get new telescopes. So as wonderful as Hubble is, there is James Webb, which is coming along. James Webb is different. It will operate in the infrared. Hubble works a little bit in the infrared. James Webb will work a lot in the red. It will see deeper in the universe, but it's a different energy regime. So it's complementary. Hubble is the only telescope that has ultraviolet and as far into the visible, with the exquisite image quality that it has. So Webb will be a complement. They will work well together. Roman will be is the same kind of mirror. There were 3 mirrors made, 1 Hubble and 2 for NSA, and NASA has them both now because the NSA never used them. So it's a 2.4 meter telescope mirror. It's exquisite as well. But it is going to be outfitted with an instrument which is going to be 1,000 times faster than the instrumentation that we have on Hubble now. And I have no doubt that by the later in the 2020s, it will supersede the science that Hubble did. Although Hubble still will have the check mark for the ultraviolet study. So we're concentrating on those now.
Great answer. Just to jump in a little bit about Roman, I work in instrumentation, so I spend a lot of my time thinking about new technologies and techniques, and knowing what some of the detectors are and instruments that are going to be on the Roman Space Telescope. I mean, it is leaps and bounds. You go from effectively 1 chip on Hubble to an array of 20. And that means you can go much faster and do lots of exciting things. And if you think about it, even the last servicing mission was 20 years. It's getting on for many years now. It's a decade ago. And technology advances. Cell phones advance. So putting new technology in there, you have to decide when you sort of need to cut your losses and move on. There's been another couple of questions that sort of link to what are the advantages and changes from Hubble to, James Webb? When James Webb is up there, what is Hubble's speciality become? How are they sort of unique, complementary, and sort of what is Hubble's role once James Webb is sort of looked? Because it's sort of seen as the successor, but it's similar, but it's also very different.
And it's I don't know where the successor thing came from. I think it was a ploy to worrying about the gyros. If the gyros failed on Hubble, what else do we have? Well, we have James Webb. Well, James Webb will not do the ultraviolet and will not do the blue portion. And that is higher resolution than what James Webb will be able to do in the infrared. So the James Webb is really, it was made to be a very large mirror, which it is. It's a deployable mirror, so it's a new technology, but it's mostly going to be in the infrared. I think it also, because it's bigger, it will look deeper. It will look deeper than Hubble ever can, even using our gravitational lenses. Let me check. I have a puppy who's outside who needs to come in because it's cold.
No, that's all right. So I'll follow in from that. I mean, James Webb is going to look at longer wavelengths than the visible light we can see, whereas Hubble's speciality is really focused on the visible wavelengths that our eyes can see. That's where it's done a lot of things. So Hubble has studied from the very close by in the solar system to stars in our galaxy, to nearby galaxies, to the most distant galaxies all of the way. And the problem is when we look further and further away, things get dimmer and dimmer, which means you need a bigger telescope, but also the light changes from visible light that we see in stars. It gets stretched out, what we call redshift as astronomers, into the infrared. So James Webb is going to be really good at looking faint things a long, long way away. That's one of the things it's really designed to do. So, whereas Hubble has able to study things closer, and James Webb will be able to do that, but they have unique science. Hubble was designed for studying the distant galaxies and the expansion of the universe. And it's been able to do this wonderful stuff. And James Webb will be the same, but they're sort of complementary, but also different because they were designed for specific science. We'll talk a little bit about some of the science things that they're good for in the event tomorrow.
In addition to the expansion, also there's a lot of dust in the universe, and so James Webb will be able to penetrate that because the infrared light will go through the dust, whereas Hubble cannot see some of these dusty regions. So for example, in these star formation regions and also out in the distant universe, there's a lot of dust. And so James Webb will help with that. Another thing is that a little complementary is that when you're looking at really distant galaxies and trying to understand them, one of the questions is, are those galaxies really like the galaxies that we see nearby, or are they different? How are you going to answer that? So you look at the nearby galaxies with Hubble and then imagine them redshifted and look at them in James Webb and say, oh, is this the same kind of animal or is it different? So when did black holes form? When did active galactic nuclei form? Did galaxies form by merging? All those kind of questions, which we won't be able, we have hints with Hubble, but we will be able to look at those questions with James Webb.
Great answer. A couple of other things. So someone asked about, 31 years of operation. So is that from the launch date or the deploy date? And how long do we think Hubble's still going to be functioning for? And I mean, that might be a question for tomorrow for Tom. But Hubble is not going to last forever. How long do we think it's going to be, and how long has it actually really operated for with the fixes for the optics and things?
Right, the launch in April 1990, the mission was only a week long. So you're picking nits, whether you the 31, it's plus or minus a week. Okay, so it's 31 years. And we celebrate the anniversary on the 24th of April, which is the deploy date, I believe. Yeah. And it worked. pretty soon after that. James Webb is going to take 6 months to sort itself out. It's going to launch. It takes a long time to get it to its parking position. And then a lot of things have to be tested. It has to unfold. The sunscreen has to unfold. It has a lot of complicated things that have to happen to it before any light hits the mirror. Whereas Hubble was a conventional telescope. You open the mirror cover, you got an image. So the engineering part of it was relatively quick. So we're dickering over a week out of 31 years. So 31 years it's been in operation, counting on April 24th of this year.
So coming back,
how long is it going to last? Okay, we keep saying, well into the 2020s. So the limiting factor right now is the gyros. We believe that one or more instruments will be working in 2025. God willing, knock on wood, whatever you want to pray for or whatever. If like the batteries last, the power, we don't have any engineering data that would suggest that any of those are degrading. And the gyros, they go through these periods of times where they're really finicky and fussy and misbehave. Right now, we're enjoying a period where the gyros aren't so bad. We've also done a lot of tests. There are 3 gyros. We've done tests where we can actually operate on one gyro. The image quality won't be quite as exquisite, but we can do science with it. And if we have instrument failures, we might have some detector failures, but we don't believe that all the instruments on Hubble are going to be gone by 2025. So we're thinking that there's going to be a nice period of time where the cousins, James Webb and Hubble, work together for a while, and we're fingers crossed, hoping that Roman will go up, and who knows, maybe Hubble will still be operating. We have no reason to believe it's going to stop. So
it's good. It's going to be a
story, and we're sticking to it.
It's going to be very exciting if we manage to have all of them. So fingers crossed.
Yeah.
A couple of sort of other questions. You know, you showed a lot of images and things like that, and there's some very famous ones as well. Do you happen to, and this might be something to ask Tom tomorrow, because there's a lot of information about Hubble and no one's an expert in all of it. Do you know which is sort of the most successful instrument, or thought of as the most successful instrument for Hubble in terms of science?
You know, it kind of depends on what year you're talking about. Wide field camera 2, of course, right after the telescope was fixed, was used a lot. The advanced camera for surveys then was kind of in the next epoch. So the imaging cameras have been very productive. Right now, the advanced camera for surveys still works. Wide field camera 2 was taken out. So wide field camera 3, it was installed in 2009 at the last servicing mission, and it seems to be a real workhorse because it has multiple channels. So that a lot of the imagery you see these days, but I will comment that there's a new sort of I'm watching a kind of a new wave of science, which is looking at objects that change over time. And so if you have the advanced camera for surveys, and we actually know how to calibrate the wide field camera 2, we'll pick 2 data against ACS, and then ACS and wide field camera 3, is that you've got very well calibrated instrumentation, and you can look at phenomena that have changed over 30 years. There are very few telescopes that have had that consistently well calibrated instrumentation over that time period. So there's starting to emerge this desire to look at things that, you know, nebula that have expanded, things that have varied, all that kind of stuff. So Hubble's getting some new science from that. And in addition, we have spectrographs, which divide the light up into, you know, the individual colors or wavelengths or energies, however you want to think about it. And now we're trying to do diagnostics on exoplanets, diagnostics on galaxies, diagnostics on star formation. So all of those are very productive. And I would say scientifically, the spectroscopy and wide field camera 3 are doing real, probably if you did a bar graph, the most. I mean, when we have the call for proposals, those instruments are all in high demand. Press releases, we do a lot with spectroscopy, but the most popular things are the solar system and imagery. It's what the media can sell, basically, and it's what people like. So popularity is mostly imaging with some amazing spectroscopy. Scientifically, there's more spectroscopy going on because all the instruments are tremendously productive. And we have 1,000 refereed papers a year, which has never been seen in any science.
It is
science.
it's truly phenomenal. I mean, one of my favorite images that I've seen, there's some of the pillars of creation, which is obviously very famous, and there's the old images that were taken initially and the newer images, and you can see changes in them. And without showing, it's hard to put it in context, but you're seeing changes on the scales of solar systems in these clouds of gas. Yeah, and it's really incredible to see those kind of things.
I did those observations, and we were doing the news release on it, and we had a scientist working with us who was very familiar with it, because we wanted to do the infrared to show that with wide field camera 3 we could see into the heart of the pillars, and all of a sudden people were going, "Look at that! We actually saw it change." And everybody was kind of stunned. It was like, "Oh my God, look at that! 25 years later."
Yeah, the universe is very old. Things change slowly in astronomical terms, so it's quite a thrill when you can actually see something change. So, and there's going to be lots more of that coming up in the next decade of astronomy. We're really pushing to looking at, not the static universe that we tend to think about, but everything's moving and changing, and trying to catalog that a lot better. So, I've got two more light-hearted questions, and then I think, unless there's any final questions, we'll wrap up. So the first one is, what kind of dog do you have?
Yeah, really hard. I have a 12-year-old chocolate lab. She's rescue. She's has been very active. She's done agility, nose work, stuff like that. Unfortunately, on the 26th of December, she got vestibular disease, which is vertigo, and she's recovering from that. So that's a challenge for us, but the personality's back and appetite and all that. She's just, try walking around for a month with your head like this. It's not real easy, gives you neck pain, so she's got that, but we're trying to get her back. And then before COVID, I adopted in December another chocolate lab, dark chocolate. She's about 95%. Her color is 95% chocolate. And I adopted her. She's a rescue as well. I adopted her in a moment of weakness as a puppy. So she's now 15 months old, and she's a holy terror. And I have to say, I'm really happy with doggy daycare, because the puppy goes to doggy daycare a couple of times a week. And I'm embarrassed to tell my colleagues who have children who are in middle school, because they're going out of their minds because their kids aren't in school. And I'm like, my dog's in school and she's happily playing all day. That's what I said.
Oh, there you go. Well, I'm hoping that your older one is on the mend soon. The final couple of questions. There was one question that came in a little bit about orbits and things and technical details. I think I'm going to punt that one to tomorrow, because I think that's a good question to some of where the observatory and things goes. So Jim Spencer, come back tomorrow and we'll answer that question then. Just to summarize, what is your favorite Hubble image? If you could pick one.
Good question. And the best answer I've ever heard is the last one. I don't know. I have, the thing is that I'm a star cluster person. So Westerland 2, I really enjoy. Also, I like Westerland 2 because I worked on it, and also, and I showed you Westerland 2. I have a project to create 3D prints of Hubble images for the visually impaired, for students with blindness and visual impairment. And Westerland 2 is one that I was able to produce. And Westerland 2 is so striking that if you look at the, we do one color because the students can't see color in the 3D prints, but the gray printout, if you look at the gray printout and you look at Westerland 2, you can see that that's the star cluster. So I love that star cluster, but I'm also a fan of globular clusters. I like them. And everybody always goes, oh, so boring. We're not going to do a press release on a globular cluster. I'm like, yeah, but they're so magnificent. They're so amazing. They have tens, hundreds of thousands of stars in them. And they all,
Yeah, I definitely agree. I think the thing I always encourage people to do, there's a huge number of images released for the 30th anniversary. If you just go online and search, you can find all of those. And the thing is, all of the images are really pretty to look at. But I encourage you to read about what you're actually looking at, because yes, they're stunning images of the universe, but there's a huge amount of science in there. If you see globular clusters, they'll look like a bunch of stars together, but you'll see different colors. And that tells us about the temperatures. It tells us about the age of the stars, where they've gone, where they're going to go, how they're going to evolve. There's a huge amount of science in there. And that's actually kind of a little segue into tomorrow, because we're going to delve a little more into some of the science tomorrow with some scientists that use Hubble data. They'll tell us, what do they get? How do the observations they get? What do they do with it? How do they, analyze it? How do they piece it together? What it tells us about the universe. So that's going to be tomorrow. I'm just going to quickly show the slide for that. So that's going to be 6 p.m. Again, on Zoom and YouTube. You can find all of the information at nduniverse.org. And then we'll be back again on Friday with a talk from former NASA astronaut Michael Good. So all there is left for me to say is a huge thank you to Carol. It's been great having you to give us an introduction to Hubble and answering the audience's questions. This talk, if you want to go back and watch it again, will be on our YouTube channel. So you can search for it under Our Universe Revealed. So that'll be online either later tonight or tomorrow. You can also find recordings of other astronomy talks and physics talks we've done as well. So hopefully see many of you tomorrow. Thanks again, Carol. It's been great. And for everybody, stay safe out there and hopefully see you again back online.
All right.
Thanks.
Be safe, everybody.
Bye-bye.
Take care. Bye.